It's my pleasure to introduce you today to Dr. Mariko Oue, who is going to give us a seminar on Snowfal microphysics. But before we get into the details of the presentation, a little bit of her background. Mariko graduated from Nagoya University, Nagoya, Japan, back in 2010. She spent a few years as a postdoc at the same institution, and then she decided to do the big jump to the US. And the first destination was Penn State University, where I think she worked with a very eclectic group of scientists at the Department of Meteorology, where he stayed there from 2012 to 2015. And she was an excellent finding for our group, the radar group, at the beginning, back in 2016, and she's been with us since 2016. Her contribution is invaluable. The way she had helped us to actually utilize our sensors to improve our visibility, to work with students, has been surpassing any expectation of my have. She's a hard worker, very intelligent, and she's going to see that from the outcome of this presentation. She is right now the lead of our fixed facility. If you pass by the South P lot, you have seen the facility of the radar. She is the lead of this facility, scientifically leading that and the operations. That same facility was very recently, last month, assigned by NSF as a community facility, so it can be requested for nationwide or international deployments. So she's going to be leading this effort as well. Mariko is also well known outside of the SoMAS family. She's well known in the Brookhaven National Lab. She's well known in the DOE and NSF now. She is a PI of 2 projects and co-PI in 4. And this seminar is part of her application for promotion to research faculty in our department. So with that, I would like you to join me to welcome Mariko to this presentation. Thank you.
Thank you for introduction. Can you hear me? Okay, I'm wearing a mask, so I'm really worried about this. So first, thank you for giving me the opportunity to present my recent research about the microphysical characteristics of snowstorms observed by the multi-radars from the Stony Brook Radar Observatory at the South P lot. First, I'd like to thank all collaborators, Brian, Pavlos, and all of the people across the world. Before starting my presentation, I'd like to repeat my history. I graduated at Nagoya University in 2010 in Japan. I worked there as a postdoc for 2 years. And then I decided to move into the United States in 2012. First, I have a postdoc position at Penn State University, where I was working on microphysics, the Arctic microphysics of Arctic mixed phase cloud using DOE radar and the radar measurement. Then I moved into the Long Island in 2016 to work at the Stony Brook University. Right now, I am a research scientist and PI of SoMAS for 2 years. So this is the outline of this presentation. First, I'd like to explain my motivation of this study, and including radar observations, radar techniques to observe the microphysics in order to identify ice growth processes. And then a little bit to talk about the result of my joint analysis and the summary. And the rest of the time, I'd like to a little bit explain about my future work at SoMAS. I have 2 kinds of motivation for this study. First one is to understand ice particle formation processes and growth processes in snowstorms, because the snowstorms around the United States and Northeast coast provide a variety of ice particles, which have a different degree of riming and aggregation. And this figure is from the Briar's work, showing the very different kind of particles within the storm, depending on the location of the storm and depending on the storm evolution. This is meaning that there are very complex microphysics in the cloud, and each particle has different particle properties like density, size, shape, force speed, whatever. So our questions are how do the ice particles form in the cloud, and where and what ice processes dominate? This complexity in the microphysics and the ice particle properties in the cloud impact the snowstorm prediction. This is one snowstorm case of last year. Figure left hand side shows prediction, the forecast, 1 day before forecast, and the right hand side is showing the observation snowfall amount at the observation site. Comparing both figures, well, looks nice, but when you look at it in detail, forecast shows the peak of the prediction is a little bit south compared to the observation. And also the prediction underestimated the maximum amount of the snowfall for. So it is challenging to accurately predict the location and amount of snowfall. This is because of a complexity in the particle properties. The snow accumulation rate depends on the particle properties such as the particle for speed, density, and size. A figure right hand side shows the relationships between force speed and maximum diameter for different types of particles. For example, this line represents the line dendrite particles, crystals, and this line represents the global particles. As you can see, there are large variability in the force speed depending on the size for each type, different types of particles. These ice particle properties are controlled by ice microphysics. So what ice microphysics are dominated in the cloud, in the snowstorm? There I'm showing the 3 different major ice growth processes here. First one is riming, where particles are grown by collecting supercooled liquid droplet, producing global particles. The second one is depositional growth, where the particles are grown by the water vapor diffusion, producing single crystals like this. And the third one is aggregation process, where the particles, individual crystals are aggregated each other during falling, producing large snowflakes like this. It has been challenging to identify these types separately observed by radar measurement. Particularly separation of riming and aggregation by remote sensing measurement is challenging because for both processes, radar reflectivity increasing and also force speed increase associated with size growth at the same rate. So there are several techniques using the radars to observe these microphysics. Here I'm showing the 3 different types of radar techniques to observe the ice microphysics. First one is Doppler velocity from vertical pointing measurement, which is sensitive to density and size. And second one is your wavelength ratio of radar reflectivity from more than 1 radar, which is sensitive to size. And third one is polarimetric radar measurement, observing the shape of particles. I'd like to a little bit more explain about each techniques, showing some examples. First one is the Doppler velocity from vertical pointing measurement. The Doppler velocity from vertical pointing measurement is attributed to particle force speed and also vertical air motion. And this particle force speed has a good relationships with radar reflectivity. The figure right inside is showing the good relationships between force speed versus radar reflectivity for different types of ice crystals and ice particles. For example, this line, the lower line, represents the plate-like crystals. And for this line, the upper boundary line represents aggregate particles, meaning that aggregate particles have a faster force speed at same radar reflectivity compared to the crystals, the single crystals. So we can use these kind of relationships to identify ice particle types. So then the second technique is dual wavelength ratio. There are different types of radars in the world. They have different frequencies depending on their need. The top is showing the spectrum diagram, frequency spectrum for radars. Left side showing the longer wavelength, and the right side the shorter wavelength. So I'm showing here the different types of radars in the world. For example, next-rad radars from NWS use the S-band. S-band radars here, this wavelength, which is a 10 centimeter wavelength. This wavelength is very good to observe the wide area of precipitation with less acceleration. Some radars also use the C-band and X-band, little bit shorter wavelengths to observe regional precipitation areas. Stony Brook radar, here I'm showing the 3 Stony Brook radars here, 1, 2, 3. They are using little bit shorter wavelengths called cloud radar, like K-band, Ka-band, and W-band. They are more sensitive to tiny particles and also sensitive to cloud droplets. So these shorter wavelength radars are very good for the snow observation. So these frequencies, different radar frequencies, different radar wavelengths has the different scattering cross-section depending on the particle size. This figure is showing the radar backscattering cross-section as a function of diameters. And the different color lines represent different wavelengths. Red line represents X-band, green line represents Ku-band, blue is Ka-band, and W is bracket W-band. K and W are our Stony Brook radar frequency. But you can see for smaller particles less than 1 millimeter, the backscattering cross-section are increasing with size for same way as a linearly like this. This is a very scattering region. But for larger particles, particularly for shorter wavelength radar, backscattering cross-section a little bit lower compared to the longer wavelengths. We call it mean scattering or non-Rayleigh scattering. This difference in the backscattering cross-section between the radar frequencies can be used to identify particle types. In particular, if we have three frequency radars, they are very useful to identify ice particles. This is the DWR versus DWR diagram. The DWR here is the dual wavelength ratio, which is a radar reflectivity difference between the radar reflectivity from longer wavelengths and shorter wavelengths. This diagram is showing the x-axis, y-axis is DWR from X and Ka, and x-axis DWR from Ka and W bar. And each line represents different types of particles. As you can see, there are the relationships between two DWR ratios of different futures depending on the particle types. For example, blue line represents aggregate particles, and red line represents global spherical particles, and black line represents the single crystals. So we can use this kind of this kind of diagrams to map our data sets to identify the particle types. Third one is polarimetric radar capability. Polarimetric radar transmits horizontally polarized waves and vertically polarized waves and return the signal, receive the returned signal from horizontally polarized wave and vertically polarized waves. The difference between these signals can be used to identify the particle properties. For example, GDR is differential reflectivity, which is a difference between the backscattering cross-section from horizontally polarized waves and vertically polarized waves. This parameter is sensitive to aspect ratios and bulk density of larger particles. So if we have overrated particles, GDR becomes positive. For example, the plate-like crystals. And there are spherical particles in the cloud, GDR becomes around zero. Therefore, correlated particles, such as conical globals, GDR become negative. So we observe the nice GDR parameters from the radar measurement. This is RHI, the vertical cross-section measurement from X-band radar. Y-axis is height and X-axis is distance from the radar. The color represents GDR. As you can see, there are very large GDR near the cloud top, and then GDR values are decreasing towards the surface, meaning that there are the plate-like crystals near the cloud top and nucleated the plate-like crystal near the cloud top. And they are aggregating each other during the falling, producing larger snowflakes near the ground. Similarly, KDP is a specific differential phase. Similar to GDR, KDP is also sensitive to aspect ratio, but also mass. The KDP is the ratio KDP is the difference between the phase, not the power. So it's also sensitive to aspect ratio, but also mass. The behavior is similar as DWR here, and also the Casper observed nice KDP signatures in the snowstorms. This figure is showing RHI vertical cross sections, y-axis is height and x is distance from the radar. Here. And as you can see, very large KDP is generating cells and 4 strips, meaning that generating cells and 4 strips produce a large amount of ice particles. Okay, so objectives of this study are first to identify the growth processes, ice growth processes in the snowstorms. Particularly, I'd like to try to separate rhyming and aggregate signatures in the snowstorm. And second objective is to integrate these different types of radar techniques to develop the robust and sophisticated technique to identify the particle types and signatures and processes. Okay, this is a Stony Brook Radar Observatory. The Stony Brook Radar, Stony Brook University, SoMAS, has a powerful observation site at South Parking Lot. You may see the some fenced area with a big radar at the South Parking Lot. The flagship radar of this observation site is K-band scanning polarimetric radar, Casper. It's this one. This radar has a polarimetric capability as well as radar reflectivity and Doppler velocity. We also have 2 profiling radars. One is MRR Pro, Micro Rain Radar Pro at K-band 24 megahertz, which can measure the radar reflectivity and Doppler velocity. And the other profiling radar is W-band profiling radar named Roger, measuring also reflectivity and Doppler velocity. This radar measurement can be complemented by the speedometer radar measurement and also the ground-based in-situ measurements like precipitation gauge, mass snow camera, and possible disruptor. Okay, let's go back to the frequency diagrams. Talking about our Stony Brook radars. The Stony Brook radars, but the MRR Pro is K-band here, and Casper is Ka-band here in the middle. And Roger is W-band, which is 3 millimeters wavelength here, for shorter wavelengths. The K and Ka-band are a little bit close each other. So let's checking about the capability of these triple frequency radar measurements first. This is the DWR versus DWR dual wavelength ratio diagrams from 3 frequencies. I'm showing the scattering calculation model result. Y-axis is DWR from K and Ka-band. K and Ka-band. X-axis is DWR, dual wavelength ratios from K and W-band. K and W-band. That's separation. different color lines represent different types of particles with different Riming degrees. And color shade represents the mean diameter, mass weighted mean diameter. As we expected, the DWR increases. Both DWR increases with the particle size. However, well, all of lines are very close together, and it is difficult to separate the Riming degrees. This is because K and Ka band frequencies are not sufficiently separated. In other words, to utilize these DWR capabilities, we need frequencies which are separated enough. However, if we introduce the mean Doppler velocity capability to the DWR measurement, these lines are completely separated. This is showing the same model result, but y-axis is DWR from Ka and W band, and x-axis is mean Doppler velocities from Ka band. The negative value represents the downward motion. But you can see there are three clear separations, three groups. One is right Riming, a middle one is medium Riming, and the other most left plots are heavy Riming. It is very interesting. So we can apply this theory, into our observation, VR observation here. This is a nice snowstorm case observed in, I think, 2019 at the Stony Brook Observatory here. The top figures is showing the radar refractivity from Roger W band profiling radar. Y-axis is high, x-axis is high. You can see nice snowfall streaks like this in the cloud. Large reflectivity means large particles and large amount of snow particles. Bottom figure is showing the DWR from Ka Caspar and W band radar. The DWR are intensified depending on the particle size. At the surface, snow camera observed nice, very nice, beautiful pictures of particles. Here I'm showing the blind crystals. This is six branches and particles that grow. If this particle is right in this backward liquid droplet. And this is a little bit complex shape, but maybe the blind aggregate particles. So this is very common. These are very common particles in this region. I am really surprised that all of the particles, most of the particles are right, but also aggregated, which means that there are complex microphysics in the ground. So let's check the DWR capability from triple frequency measurement first. Right, the top panels show the DWR versus DWR diagram from the three radar. Line represents scattering calculation as I showed before. Color shade represents the occurrence of data set. Our data followed scattering calculation models very well. However, as we expected, it is difficult to separate the aggregation and Riming processes. But if we include the mean Doppler velocity capability here, we can separate the processes clearly. This diagram is showing that a DWR versus a mean Doppler velocity diagram. So y-axis is the DWR from Casper and double band. Casper and Roger, the double band radar. The lines represent the scattering model calculation, the theory. And the color represents the occurrence of the dataset from our dataset. As you can see, there are two distinct data populations. One follows pink and red line representing right lining, and the other follows in medium lining lines. It's complete separation. Interestingly, this theory also works with the different pair of DWR and DWR. Right inside shows the same dataset, but y-axis is DWR from K and Ka band. K and Ka band are very close frequencies. As I showed before, it is for the processed frequencies, DWR theory doesn't work well. However, if we use the mean Doppler velocity here, the data sets are clearly separated depending on lining degree. This is very interesting and very useful. And we also have a polarimetric radar variables. Adding polarimetric variables include more processes in terms of the shape, depending on the shape associated with particle growth. Here I'm showing the same diagram, same DWR versus mean Doppler velocity diagram. But color represents GDR in left hand side and KDP in right hand side. As I explained before, the GDR represents the shape parameters, and KDP is also sensitive to shape and also mass. Looking at the GDR in left hand side, following this right lining line, GDR value decreasing with size. DWR value is decreasing with DWR, meaning that aspect ratio increases with size associated with aggregation process. Looking at KDP, along these lines, KDP values didn't change much, which means that the ice water content didn't change with size growth, just the size growth with aggregation process. We can also see more detailed growth processes within the Fallstreaks by looking at the different height of the Fallstreaks. Here I'm showing the same DWR versus mean Doppler velocity diagrams for different height of the Fallstreaks. Region A is near the cloud top, and region B is the lower altitude of the Fallstreaks. First, looking at higher altitude region A here in the right middle panel. So, color represents GDR in this plot, and GDR decreases with the DWR, meaning that aspect ratio increases with size growth. And most of the data set follow the right lining, and some data sets are a little bit shifted toward medium lining, meaning some initial lining. One interesting signature is that GDR values a little bit increased towards the lining signature with the lower GDR values here, both for smaller particles. which means that this is a typical signature of initial rhyming of ice particles. For the region B in the lower altitude, the more data sets are shifted toward medium rhyming and heavy rhyming. And the GDR value will be decreased, meaning that particles become more spherical with aggregation and also rhyming processes at lower altitude. Okay, let's summarize my analysis here. First, the DWR versus Doppler velocity diagrams exhibit a distinct separation of different time degrees and particle growth processes in the snowstorm. The figure, the cartoon right inside is a summary of my analysis in one panel. This is very useful. Red line represents aggregation line. Blue lines represent rhyming processes. So I also plot the GDR-10 KDP signature associated with aggregation and rhyming. We can use this kind of diagram to map our data set to identify which particles dominated and which processes dominated in the cloud. And the polarimetric observables provided further information to distinguish aggregation and rhyming processes. And particularly in one case study showed that aggregation dominated in higher altitude of Fallstreaks and rhyming dominated in lower altitude Fallstreaks. So this is my summary. And the rest of the time, for 5 or 10 minutes, I'd like to little bit explain my plans at the SoMAS as an assistant research scientist in the next step. I have two kind of objectives for our plan, the future plan. One is to beneficially use a Stony Brook Radar Observatory, multi-sensors from Stony Brook Radar Observatory. I want to facilitate my analysis by integrating all of multi-sensors from Stony Brook Radar Observatory to understand more dynamics and microphysics of the cloud, and also retrieve accurate geophysical quantities. We are operating not only Stony Brook Radar Observatory at ground-based site, but also the mobile tracks, including X-band phase array radar, soundings, and other ground-based instruments as well. The flowchart in the right inside is showing an example of how we can beneficially use the multi-sensors to estimate accurate snowfall. The multi-ground-based sensors like Pascal, mask of snow camera, and fluvial wave precipitation gauge can estimate mass diameter relationships of snow particles. This can improve the estimation of snow accumulation S. And using the radar observation, we can estimate the improved refractivity versus snowfall relationships. This can be evaluated by the microphysics and dynamics observed by radar and radar measurements. Vice versa, these observed microphysics can also be evaluated by the SDS relationships as well. And second, these observational data set as well as retrievable data can be shared with a wide range of atmospheric science community. Specifically, I'm planning to improve our real-time monitoring website. This is the current real-time monitoring website. I'd like to improve this website so that the user can customize the display, like zoom up, zoom in, and zoom out, and changing the color bars, changing the period. And also arranging, I'd like to arrange the data archive site. This is the current data archive site for impact phase, which can be shared by the many communities like Oklahoma University, Penn State, and North Carolina State University, and in the world. I'd like to include more retrievable data sets, not only observational data sets, like wind, ice water content, liquid water content, and breathing data set. And also, I want to rearrange for more user-friendly, so that the user can set up the range of the period, and downloading the specific data set. And finally, I'm planning the virtual tour and virtual lecture of the remote sensing observatory. This is the current virtual tour created by Mark. I'd like to improve this virtual tours by adding the pop-up picture, one nice pop-up picture, pop-up detailed description for each instrument. And also I'm creating the videos to explain the analysis and each sensor. And then finally, we can use this virtual tour for the virtual lectures for the local community, not only local community, but also other universities outside the state. The second objective is to bridge the gap between model and observation. The cloud models are very useful to understand the physics, but cloud models still need to evaluate using the observations. Vice versa, observation requires cloud models to better understand physics. However, these products are very different. For example, cloud model provides the geophysical quantities like wind and ice water content, liquid water content. But the observations, particularly remote sensing observation, provide remote sensing products like radar reflectivity, mean Doppler velocity. So these comparisons of different parameters include large uncertainties. To resolve this issue, we have been developing the cloud resolving radar simulator, CRSIM. The CRSIM simulates the radar parameters like radar reflectivity, mean Doppler velocity, DWR-DV from the cloud model. This allows us first to allow for the apple-to-apple comparisons to evaluate model simulation. In different ways, by comparing the virtual observational product from simulators with cloud model again, we can address the uncertainty in observational product due to the sampling limitation and some limitations in the observation. This is an example analysis, example analysis using CRC. Top left top shows cloud fields simulated by cloud models. And bottom panel shows the simulated radar cloud field, assuming that radars are located at the center line. I'd like to say that radar cannot observe all of the cloud because of the sensitivity issue, the sampling limitation. So this impacts on the cloud fraction estimate first. This is the cloud fraction profiles from simulation. Black line represents truth from models, and color line represents simulated observations with different sampling strategies. So this figure shows that we need longer sampling time to capture the correct cloud fraction profile. So we also estimated the uncertainty vertical profile and retrievals. The black line represents truth, and color lines represent simulated observation. You can see there are big errors in the higher altitudes because of the sampling limitation. We can perform this kind of analysis before the field campaign to optimize radar deployment and quantify uncertainties before the field campaign. This can lead to the better comparisons with models for more better understand the issues. Okay, that's all I have. Finally, I'd like to acknowledge all of the support. So thank you for your attention and coming here. I'm taking any questions and comments.
Okay, thank you so much, Mariko. My only comment is that Mariko saw what she does in 1/4 of her time. She does many other things. Great interest to her was here. Questions for Mariko? Well,
So, very nice talk regarding rhyming versus aggregation. Are they theories to describe under what conditions, say, the particles tend to grow by rhyming and the other conditions?
Yes,
tend to aggregate?
Yes, of course. Rhyming requires supercooled liquid droplet in the cloud. We need other instruments like LiDAR. We have a LiDAR measurement which is sensitive to the supercooled liquid droplet. So we need to check where the supercooled liquid droplet is there and how the supercooled liquid droplets can work to produce rhyming or something. I didn't show detail here, but for different cases, the rhyming generally happens when we have more south flow dominated in the snowstorms. I assume that I hypothesize that some wet air mass came from the ocean side to provide the enough water vapor to create the supercooled liquid droplet. Therefore, when the aggregation process dominated, one northerly front dominated, which is a little bit colder, a little bit drier. This is one case study where we need a check analysis, but good.
Thank you.
Thank you so much for your talk. Yeah, kind of following up on that question, have you been able to relate the aggregate or the particle properties in relation to like isotopic studies, like in particular like oxygen isotopes? I'm just thinking of ice core studies and looking at those, O16, O18 ratios. Has that been done in relation to these particles?
Yeah, we have a nice snow camera, Manjango snow camera in the collaboration with North Carolina State University. This takes a picture of snow particles, individual snow particles. and basically aggregates more fluffy and more roughness in the shape, and also less rhyming, less superfluous liquid droplet signature, and slower for speed compared to the rhyming, like the particles. Basically larger size rather than the global particles.
Yeah, that's what you mentioned at the different altitudes.
Yes. Yeah, showing, observing these ice properties in the different altitudes is a kind of still challenging. That we, as I showed today, we need a more remote sensing measurement to see, to look at the force speed, size, and shape. Shape means aspect ratio. Aggregate has a lower aspect ratio, basically averaging 0.6. Global particles are more spherical. But it's still good challenge.
There's one slide very interesting, showing snow falling down from about 12 kilometers.
The time height cross section.
Yes. Oh yeah.
That's
Okay.
one.
This from like 8 kilometers.
Yeah,
Wondering, did the reader see or observe any of the distribution of particle size, particle speed, and different types of those particles in that vertical profile?
Yes. This is from one radar measurement. The radar only reflectivity values here. Large reflectivity, like brown and yellow, means larger reflectivity here, meaning that bigger particles and also the number concentration is large. But only this reflectivity plot, it is difficult to see the size distribution and types of particles. But if we include the different frequencies here and also Doppler velocities, then we can identify the particle types, different types.
But for this specific case, what was the sampling frequency? How the interval to sample to do the scan?
Oh yeah, that's a good point. For this radar,
Okay.
every second.
Every second.
Yeah, every
Wow.
second.
So you have the data for every second, basically.
Yeah, we have a profiling data every second. So every 4 seconds.
Every 4 seconds.
Yes. For the Casper radar, every second.
Mariko, very interesting topic. I just wonder how much the new frequency radar can improve the environment degree quantitatively, because I see most of the results are quantitative based, like
Yeah, that's a good point. My analysis here is a very qualitative analysis here. Quantitative analysis is the next my challenge. Yeah, good point.
okay, yeah, just wonder, yeah, there's you
Yeah.
said Wavelength ratio can improve that.
Yeah, that's why I'd like to integrate more data sets, not only radar, but also LiDAR and ground-based measurement, which can estimate the reflectivity versus snowfall estimate. Yeah, that's my next step.
All right, thank you very much, Mariko.